Hi, Chem 151 students. So this is going to be my third lecture of week 11, and the point of this lecture is just to walk you through some titration problems. So in the last lecture, we talked about the concepts behind setting up weak acid strong base or strong acid weak base titration. The concepts are the most important part, because once you have written the correct equation that applies to the situation in the titration problem, then the rest is relatively straightforward. It's just like the same as, what we did in chapter 17, what we did in chapter 18. It's not that much different from that. The hard part is setting up the problem correctly. And so what I'd like you to do is now walk you through some of these relatively long and time-consuming titration problems where we calculate the pH of a titration at various points of the titration. And so I want to do these types of problems along the course of a single titration for weak acid strong base and strong acid weak base. That way, for the same titration, you can see the way you would approach it for each different point in the titration. Usually when you get a problem, it will ask you what is the pH at a certain point of the titration. You identify what point it is, and then you use that information to set up the problem and perform it. But here what I'm going to show you is for each of these different situations what you would do and how you would approach them. And so going back to the previous slide set, I showed you the two steps that were involved. Step one is always a stoichiometry step, where the strong acid or base is completely neutralized. Then the next step is an equilibrium step, and the way you approach the equilibrium step depends on whether you're before the equivalence point in the titration, at the equivalence point in the titration, or after the equivalence point in the titration. So the first step is to identify where you are at in the titration, and generally that involves identifying where the equivalence point would be. And so for this first problem, I'm going to walk you through that part first, and then we will go into the approach for doing the equilibrium, the stoichiometry step, then the equilibrium step. One thing I want to mention is the way that I'm going to show you how to do this is a bit different from the way your book shows you. Both are correct, but the way I like to do these problems I find to be simpler to follow, because in the book often what they'll do is they'll take a volume and a molarity, turn that to moles, do the stoichiometry step in moles, then return those back to molarities by dividing by a new volume, and then performing the equilibrium step in terms of molarities. I find that kind of back and forth between moles and molarities to be a bit confusing. So the way I do it is I initially calculate molarities right from the beginning based on the new volume of when two solutions are mixed, and then I carry out the entire problem in molarities from there on. So you'll see a little bit of a different approach between the way your book shows you how to do it and the way I show you how to do it. I think my way is easier. My students tend to like it more, so that's why I teach it this way. However, the book way is perfectly acceptable too. It just kind of a little, kind of goes back and forth between moles and molarities in a way that I find a little harder to follow. And so let's get started now. These happen to be the same as problem 3 on your homework. For strong acid weak base, I'm going to begin the week next week with a video about that. But that doesn't mean you can't try the problem on your own. Based on the concepts that we discussed, you can actually attempt that problem before I walk you through the entire thing. But I do think that this is a giant topic. Buffers itself is a pretty big topic, and then titrations is a really big topic. And so I kind of spread it out between this week and next week. Next week we'll also talk about solubility. So let's get started on a weak acid strong base titration problem. So here we go. So here's the titration problem that we're going to perform. So a titration is performed in which 0.2 molar sodium hydroxide is added to 20 milliliters of 0.4 molar hypochlorous acid, which has a Ka of 2.5 times 10 to the minus 8. Determine the volume of NaOH that would be required to reach the equivalence point. So this is just a stoichiometry problem. Remember what the equivalence point means. The equivalence point means we're going to have a stoichiometric ratio of the acid to the base. Usually that's going to be 1-to-1 ratio. Also, after we've determined this, we're going to find the pH of the solution after no titrant has been added. And here the titrant is the sodium hydroxide being used to titrate the hypochlorous acid. And 20 milliliters of sodium hydroxide, 40 milliliters of sodium hydroxide, and 60 milliliters of sodium hydroxide. This is going to take us along the entire course of the titration from before the titration begins all the way to after we have reached the equivalence point. So let's start with the first problem. That's where you always want to start, is figure out, well, where is the equivalence point? That way you'll know if you're before or at or after the equivalence point. So determine the volume of NaOH that would be required to reach the equivalence point. This is a stoichiometry problem. So the first thing we'd want to do is think about the actual neutralization that's going on here. So here we have the formula for hypochlorous acid, HClO, with a hypochlorite ion with H+, and NaOH. So we have a monoprotic acid and a strong base. So our product is going to be a salt that is composed of the positive ion from the base and the negative ion from the acid. So sodium is +1, hypochlorite is -1, and so our salt will be sodium hypochlorite. The other product will be water that comes from the H+ and the OH-. So this is already balanced. 1 sodium on each side, 1 chlorine, 2 hydrogens, 1 oxygen. So we are going to have a 1-to-1 stoichiometric ratio. And now we simply do, this becomes a solution stoichiometry problem. So we're going to start with our 20 milliliters of 0.4 molar hypochlorous acid, and we're going to turn those to moles of hypochlorous acid. Then we're going to use our molar ratio. 1 mole of hypochlorous acid reacts with 1 mole of sodium hydroxide. And then we'll know how many moles of sodium hydroxide. Finally, we'll use the molarity to convert the moles to how many milliliters of sodium hydroxide will be needed. So we're going to start by writing our amount of our hypochlorous acid. We got 20 milliliters of hypochlorous acid. And we're going to use the molarity to convert the moles of milliliters of hypochlorous acid to moles. And so this is 0.4 moles per liter, or we could also call this 0.4 moles per 1,000 milliliters. So we make sure milliliters of hypochlorite is in the bottom, so those will cancel. And the other side here will be 0.4 moles of hypochlorous acid. And so I could put per liter here, but that wouldn't cancel with the milliliters. So I put the equivalent of a liter, which is 1,000 milliliters. This is a kind of a little shortcut that I use. Instead of putting moles per liter, I put moles per 1,000 milliliters. That saves us 1 conversion factor and kind of squeezes our work down. You are perfectly okay. It's perfectly fine if you use this shortcut like I did. Okay, next we want to go from moles of hypochlorous acid to how many moles of sodium hydroxide it reacted with. And so we've got a 1-to-1 molar ratio. Of course, we make sure that our units are going to cancel, so we're going to put the moles of hypochlorous acid down here, and the number that's going to go with that is the coefficient in the balanced equation. It's 1. Then on the other side, we're going to have 1 mole of sodium hydroxide after our hypochlorous acid cancels. That's going to get us to 1 mole of sodium hydroxide, or to number of moles of sodium hydroxide. Finally, we want to know how many milliliters of the sodium hydroxide solution that we needed to use. And so we're going to use the molarity, 0.2 moles per liter or 0.2 moles per 1,000 milliliters. So we're going to put the moles of sodium hydroxide on the bottom. That way these will end up canceling. And the number that goes with the moles is 0.2. 0.2 moles of sodium hydroxide for 1 liter of solution. Moles of sodium hydroxide cancel. Or instead we can just write 1,000 milliliters, which is the same as a liter. And now we have determined what volume of sodium hydroxide would have to be added to reach the equivalence point as soon as we finish calculating here. So it's going to be 20 times 0.4, since it's on the top, divide by 1,000 on the bottom, and then times 1, divide by 1, that doesn't change anything. Then times 1,000 on the top here, then divide by 0.2. And we get that it will take 40 milliliters of sodium hydroxide, and that would be written with 2 sig figs here. I guess technically it would be 40 with 2 sig figs. I wrote 40.0. But this isn't so bad. We did start with 3 sig figs on the original volume. Technically, it would be 40 with 1 sig fig. But that will be the point at which we reach the equivalence point once we have added sodium hydroxide. So that now that we know what volume of the base we need to add to reach the equivalence point, we can now evaluate where we are relative to the equivalence point based on how many milliliters of sodium hydroxide have been added. Okay, so now we can go ahead and do the titration problem. So for the titration problem, we're going to start at the very beginning before we have added any sodium hydroxide. So at this point, we have no sodium hydroxide in here, 0 milliliters. All we have is hypochlorous acid. And so in order to determine the pH, we're going to have to do a weak acid equilibrium, just like in chapter 15. We got 20 milliliters of 0.4 molar hypochlorous acid. The volume here doesn't even matter. What matters is our molarity of our hypochlorous acid, which is 0.4 molars. That's our initial concentration. We're also going to need the Ka because we're going to be doing an equilibrium problem. So we're going to write the acid equilibrium equation for hypochlorous acid, and we're going to set up an ice table and solve for the concentration of hydronium. So we're going to have a weak acid equilibrium problem because no sodium hydroxide has been added yet. So we don't need that first step where we do the complete neutralization of any added strong base because we have not added any strong base yet. Also, it's very common to call your weak acid HA, and to call your bases B, your weak bases. Just makes writing out the equations simpler. I'm going to regularly call my weak acids HA so that we can just write the general form HA here plus water. And that's all we've got in the flask right now. We have our weak acid, hypochlorous acid, in water. That's it. So this is the appropriate thing to write for reactants here. Always be thinking about what's actually in my flask. Those are the things that are going to be on the reactant side. There's going to be an equilibrium here because this is a weak acid. And now what's going to happen is, since this is an acid, it's going to be giving its proton over to water. That's what acids do, is give up protons, right? And so we're going to get H3O plus hydronium ion, and we'll have the conjugate base, which is A minus, which is actually hypochlorite ion. But it doesn't really matter as long as we know what the Ka is. So now it's going to be time to set up an ice table. Here's our ice table. We're going to put our initial concentration of hypochlorous acid here. So it's going to be 0.4 molar right there. And then we're not going to put anything for water. For hydronium, we're going to say it's about 0 to start. And for the anion here, the hypochlorite ion, we have none to start. And so now we're going to do our weak acid equilibrium. Because there are no products, the reaction must move forward. Q is 0, less than K, so reaction goes to the right. And so we're going to say minus X right here. Then we'll say plus X and plus X right here. All of these are plus 1X because all of the coefficients are 1 here. So our equilibrium concentration for the weak acid is 0.40 minus X. For the hydronium, it's X, and for the anion here, hypochlorite ion, it is X. So now we write out the Ka expression. So the Ka expression here is our hydronium concentration and our anion concentration multiplied on top. And on the bottom is going to be our weak acid HA concentration, and we don't include water, it's a pure liquid. And so that is going to be equal to 2.5 times 10 to the minus 5, or minus 8 rather, right here. If we will now plug in our values, it will be X for hydronium, X for A minus, and 0.4 minus X for HA. And those will be equal to the Ka, which is 2.5 times 10 to the minus 8. So now, as usual, we're going to probably use our simplifying assumption. You can probably just look by inspection. Is this initial concentration, 0.4 molar, at least 400 times greater than the Ka? Oh, definitely. Yeah, definitely. It's like a billion times greater almost, or several tens, hundreds of millions. It's definitely way greater. So our x is going to be very small. We'll be able to assume that 0.4 minus x is about the same as 0.4. So let's take this whole part here. X times x over 0.4 minus x equals 2.5 times 10 to the minus 8. Let's roll that forward to the next slide. So this is what we had here. So it's x times x over 0.4 minus x. And again, we're going to be able to assume that x is small. If we do our pre-check, it's our initial concentration, 0.4 divided by 2.5 times 10 to the minus 8. Is this greater than 400? Oh yeah, way greater. I don't even need to take out a calculator to know that. And so that means that this top part is going to be x squared. The bottom part is going to be about 0.4. Okay. And now, to solve this, we can multiply both sides times 0.4. Okay. And actually, like to instead use my Casio instead of this Windows calculator. All right, so we're right here. Okay. And so now if we multiply both sides times 0.4, so that would be times 0.4 right here, which would cancel 0.4, and times 0.4 right here. Okay. And so we get x squared on this side is the only thing left, and so I've written that right. Whoops. I've written that right here. And then on this side we have 0.4 times 2.5 times 10 to the minus 8. So let's calculate that. 0.4 times 2.5 e minus 8. And I get 1.0 times 10 to the minus 8 equals x squared. And so then I take the square root of that, square root answer, and I get that x equals 1 times 10 to the minus 4. And that is the concentration of hydronium in this problem. If you go back to the ice table. Okay, so now to get the pH, we just take the negative log of that. So the hydronium concentration, the pH is going to be a negative log of the hydronium concentration, which is a negative log of 1 times 10 to the minus 4, which is just, you actually can do this. You don't need a calculator to do this. The log cancels 10 to the power. If you multiply something by 1, that doesn't change it. And then the negative cancels the negative here, and you get that this equals 4. And if we want to technically write this with the right number of sig figs, it would be 4.00. 4.00. So the pH here is 4.00 before we have added any base. So this was just a weak acid equilibrium problem, just like what we would do in chapter 18. There was no titration here because we have not added any of the sodium hydroxide yet. It was just weak acid in water. Okay, so be careful. Read the question correctly, or carefully, right? Here, this is actually not a titration problem, even though it looks like it, because we have not added any titrant yet. It's just a weak acid equilibrium. So we don't need the first step, because the first step is all about neutralizing the strong base that has been added. But no strong base has been added. So we didn't need step 1 of our titration problems. We just did step 2, the equilibrium. So, but now we're going to start adding titrant. And so the next question asks, same titration, but now what is the pH after we have added 20 milliliters of the titrant? So at this point, we're going to have 2 steps. First step is going to be a stoichiometry step where we assume 100% reaction of the strong base until it is all gone or until our acid is all gone. And so because we have now mixed solutions though, we've got to calculate new molarities, all right? And this is where I do things a little bit different than your book. I treat the fact that we have mixed 20 milliliters of our hypochlorous acid solution with 20 milliliters of the titrant, I treat this as a dilution of both solutions because we took each solution, They were both each 20 milliliters, but when we mixed them at the end, they had a new volume, which was 20 milliliters plus 20 milliliters, which is 40 milliliters. So I perform this calculation as a dilution to begin with. And the reason why I do this is because it allows me to stay in molarities for the entire problem. Instead of converting to moles, doing some stoichiometry, converting back to molarities, so you can plug it into the K expression and so forth. That's all just a lot of extra work. So I use M1V1 equals M2V2 for each of these. My M1 for each is going to be my initial molarity. So M1 for sodium hydroxide is 0.2 molar. Okay. M1 for hypochlorous acid is 0.4 molar. V1 is the volume of each that I had. So at the beginning, I had 20 milliliters of sodium hydroxide before I added it to the acid. That's V1 for sodium hydroxide. For the hypochlorous acid, V1 is 20 milliliters. That's how much I started with. Now V2 is going to be my total volume once I have mixed them. So my V2 is going to be the 20 milliliters plus the 20 milliliters. It will be 40 milliliters. So both of these are going to be together in a solution that is 40 milliliters. And what I'm trying to find is M2. What is my concentration after these two volumes have been mixed? So this is different than the way your book presents it. I think that you will prefer this method over the way the book does it. But as I said, they both lead to the same answer. Just my way has less steps. So our total volume is the 20 milliliters of the hypochlorous acid that we started with, plus the 20 milliliters of the sodium hydroxide that we added. So the new volume, V2, the total volume, is 40 milliliters. Okay, so I've called that V total. That is V2. All right. And we've solved this here for M2. So we solve for M2. The way we're solving for M2 is we divide both sides by V2, or V total, as we could also call it. And then we get that M2 is M1 times V1 over V2. And that's what we're going to calculate, M2, for each of these. So first, again, we're going to call the weak acid HA, just for simplicity's sake. My initial concentration of sodium hydroxide is going to be V1, 20 milliliters of sodium hydroxide. That's right here. My M1 here is going to be 0.2 molars of sodium hydroxide right here. My V2 is the total volume, 40 milliliters right here. So my new concentration for sodium hydroxide is 20 times 0.2 divided by 40. That just cuts it in half. It's 0.1 molar. Okay, so this makes sense, right? We started with 20 milliliters of sodium hydroxide. Once we mix these solutions, it was now in a volume of 40 milliliters, so its concentration is now half because its volume has been doubled. Same thing for the HCl, or the HA, the weak acid. We start with 20 milliliters of the hypochlorous acid, that is V1. Its molarity, M1, is 0.4 molars to begin with. There we go, right there. The V2, which is the total volume, is 40 milliliters. That goes down here. And then we have 20 divided by 40, which is 1/2, times 0.4, which is 0.2. And so now we have the initial concentrations of the sodium hydroxide and the weak acid. So now we can do our stoichiometry part, our step 1 part, in molarities instead of doing it in terms of moles. We've been doing that the whole time anyway. At this point, all the volume change that was going to happen in this problem has already happened. So once the volume isn't going to change anymore, you can use molarities in the place of moles. Why? Because molarity is moles per liter, right? Or in other words, moles over volume. So if volume is not changing, then you can add molarities or subtract molarities the same way you would as you would moles. To give you an example with numbers, if I have 2 over 4 minus 1 over 4, that is 2 minus 1 over 4, or just 1 over 4, right? Because, and the 4 here is like our volume. So the volume did not change right here. And so we were able to add the numerators or subtract the numerators without any issues because the volume remains the same. After we've done this this dilution to account for the volume change, the volume will no longer change for the rest of the problem. So we can add and subtract molarities and in the place of moles, and it will work just fine. So now let's do our stoichiometry step. The next step is step 1, stoichiometry. This is where we would assume 100% reaction of our strong base, sodium hydroxide. So our equation for the stoichiometry is our mixture of sodium hydroxide and hypochlorous acid. So those are our reactants in the stoichiometry. Sodium hydroxide is neutralizing hypochlorous acid. So we're going to call the hypochlorous acid HA again, and we're going to keep our initial molarities that we had, and we're going to write our equation. The weak acid, HA, is reacting with the added sodium hydroxide. This is a one-way reaction. The stoichiometry is one way because we're assuming 100% reaction of the strong base. And again, as we saw earlier, our products are going to be our salt, which is sodium as the positive ion, A minus as the negative ion, so sodium NaA. And then our other product is from the H plus and the OH minus, it is water. That is the neutralization. And again, this is the stoichiometry step. So we are assuming 100% reaction of the strong base until either it is all gone or until the weak acid is all gone. One or the other is going to react completely. So we're going to, and here I'd like to remove the sodium spectator ion. It just makes it look a little cleaner because here we have sodium and hydroxide ions, which are separate. Here we have sodium and A minus ions, which are separate. The sodium ions are not doing anything. So if we remove them, we have still the HA, but now we have just hydroxide ion. And for the products here, we have just the A minus ion. So we've gotten rid of here the sodium spectator, which always makes things look a little cleaner because what we're interested in figuring out to do our equilibrium step next is how much of the weak acid do we have remaining and how much of its conjugate base is in the solution. And so that way we can perform the equilibrium calculation. So we're going to make a table. It's not an ICE table. It's a SCE, start, change, end of stoichiometry table. Okay? We're doing stoichiometry. This is not equilibrium. There's no double arrow here. We're assuming that either the HA or the OH minus is going to run out and it's going to react completely. So our initial concentrations that we determined by our dilution strategy from the first slide is that the initial concentration of sodium hydroxide or just hydroxide ions is 0.1 molar, and our initial concentration of the weak acid is 0.2. So 0.2 molar for the weak acid, 0.1 molar for the sodium hydroxide, and before the neutralization happens, we have none of the conjugate base. Remember, yes, is there some of the conjugate base in the solution for the hypochlorous acid? Yes, okay? But we make these assumptions and assume 100% reaction of the strong base so that we can go back later and deal with the equilibrium. This makes the problem doable. Without these assumptions, the math is just be a mess. So we make these assumptions in order to make the problem easier to calculate, the pH easier to calculate. It's not incorrect. It is correct. We just take one thing at a time. So one thing at a time. First, we do the neutralization for the hydroxide. So we have no product here. The reaction must go forward. So for our HA, it's going to be minus something. For the OH minus, it's going to be minus something. And we're not going to say X here because this is not an equilibrium step. This is a stoichiometry step. Our assumption is 100% reaction. And so these are 1-to-1. The hydroxide is going to run out first. So we're going to say that all of this is going to be used up. So we're going to say minus 0.1 here. That way we know there's all of the base has reacted, which means we'll also have minus 0.1 over here, and 0.2 minus 0.1 will be 0.1 molars remaining of the weak acid. And then here for the conjugate base, we're going to do plus 0.1 molar. And so we get 0.1 molar concentration for the conjugate base. And so now we're finished with the stoichiometry step. Now we are ready to deal with the equilibrium step. So let's do that. equilibrium. Again, we're continuing to call HClO HA. From the previous slide, we had 0.1 molar of the weak acid and 0.1 molar of its conjugate base. So this is what you should be thinking. We are before the equivalence point, because remember we calculated it was going to take 40 milliliters of the sodium hydroxide to reach the equivalence point. Or you can see here, we're not at the equivalence point because we still have some of the weak acid left. When we're at the equivalence point, all of the weak acid will be gone. It will be turned into the conjugate base. So we are before the equivalence point. We are in the buffer region. So we have significant amounts of both the acid and the conjugate base. Also, we have a very small Ka, as we saw earlier. So our simplifying assumption held up before we did the pre-check. It will continue to hold up. What this means is we can use the Henderson-Hasselbalch equation. Remember, to be able to use the Henderson-Hasselbalch equation to do your equilibrium, two conditions must be met. Number one, you must have significant concentration of an acid and its conjugate base in solution, a weak acid and its conjugate base. Step two, or condition two, is that your simplifying assumption must hold, meaning K must be small. It is. It's small compared to the initial concentrations, at least 400 times smaller than your initial concentrations. It is. So we are actually free to use the Henderson-Hasselbalch equation. The equilibrium we're dealing with is the weak acid equilibrium. Weak acid plus water is in equilibrium with its conjugate base, A-, and hydronium ion. Again, the hardest part is identifying what is it that's going on here. Well, what we have in here is the weak acid donating its proton to water in equilibrium with its conjugate base. So this is the appropriate equation, the K for which is the Ka. Ka of this acid, 2.5 times 10⁻⁸. Of course, we can always write up an ice table. Okay, we don't have to use the Henderson-Hasselbalch equation. So I do like to show you what's going on with this equilibrium. 0.1 molar for the HA, about 0 for the hydronium, and 0.1 molar for the A-. Since we have about 0 of the hydronium, we know the reaction has to go forward. So we're going to do minus X here, plus X here, and plus X here. So our equilibrium amount of the weak acid is 0.1 minus X. For the hydronium, it is X. And for the A-, it is 0.1 plus X. 0.1 plus X. Doesn't hurt to do the pre-check. Pre-check here is initial concentrations, 0.1 molar. Divide by our Ka, 2.5 to the 10⁻⁸. Is that greater than 400? Oh yeah, way greater than 400. Since this is a buffer, as I mentioned, we can use the Henderson-Hasselbalch equation. We know it's a buffer because we have significant concentration of the weak acid and its conjugate base, both in solution. So we're going to use the Henderson-Hasselbalch. pH equals pKa plus log base over acid. Your salt is over your potatoes. Okay. And so pKa is going to be the negative log of the Ka, plus the log of the base concentration, which is 0.1 molar. That goes right here. Divide by the acid concentration, 0.1 molar, which goes here. Now, this is the log of 1. The log of 1 equals 0. Okay? Always a good thing to keep in mind. Another reminder here, this is going to become more and more important as we move on to later chapters too, is that if you have the log of a number that is less than 1, that is going to be a negative number. And if you have the log of a number that is greater than 1, that is going to be a positive number. And if you have the log of 1, that is 0. So we're really, you might have noticed here, we're at the halfway equivalence point. To get to the equivalence point we calculated would take 40 milliliters. We're halfway there at 20 milliliters of titrant. So at the half equivalence point, the pH equals the pKa because this whole factor here goes to 0. And so pH equals pKa, negative log of 2.5 times 10⁻⁸. Let's calculate what that is. Negative log 2.5 EE, that's 8. And so the pH here will equal 7.60. So our pH is 7.60. Okay. So that is we just did a problem here where we were on the way to the equivalence point. We weren't at the equivalence point yet. So this is the way you approach the calculation before the equivalence point. Whether you're before, at, or after the equivalence point, you always do step 1, stoichiometry. That's this neutralization of acid and base, assume 100% reaction. But because we were before the equivalence point here, for the equilibrium step, step 2, we were in the buffer region. So we were able to use the buffer equation, the Henderson-Hasselbalch equation. I always like it when that happens. Real quick and easy. Plug those concentrations in there. You don't even have to draw the ice table if you don't want to. I just thought I'd draw it out just to show you what it would look like. Of course, remember the Henderson-Hasselbalch equation is just another way of writing the Ka, plugging in these equilibrium concentrations, solving for X, taking the negative log of that to get the pH. That's the other way of doing it. Works exactly the same. This is the shortcut, Henderson-Hasselbalch. If you know you're in the buffer region, you can skip all this and just go boom, plug this in, plug this in, boom, plug this in, boom, plug, take negative log of K, just plug this all in, and boom, you get right to the pH. The time you're allowed to do this is when you have a buffer, significant concentration of acid and conjugate base, and when your pre-check works out, when you have a small enough Ka to do the simplifying assumption. So that's the way to handle a strong base, weak acid titration before the equivalence point. Next is when we add 40 milliliters of titrant. So that's what's different here. We already calculated that when we added 40 milliliters of the sodium hydroxide, that was when we were going to reach the equivalence point. But let's say you hadn't calculated that beforehand. You will still find out that you're at the equivalence point. Let's go through the same process. It's going to be exactly the same. We're just going to end up being at the equivalence point. So our equilibrium step is going to be different because it's our equilibrium step. The way you approach it depends on if you are before the equivalence point, at the equivalence point, or after the equivalence point. So in the last one, we were before the equivalence point. So we used the Henderson-Hasselbalch equation. Let's see what happens here. So our first step is the stoichiometry. We have to figure out what the initial volumes here of the sodium hydroxide and the hypochlorous acid are. So just like last time, we're going to find the molarity of each of these, hypochlorous acid and sodium hydroxide, by taking M1 times V1 over V2. And V2 is our total volume of the initial acid solution plus the titrant. So our total volume this time, V2, is 20 milliliters of the hypochlorous acid plus 40 milliliters of the sodium hydroxide titrant. We have a total volume of 60 milliliters. That's our V2. Now for the sodium hydroxide, again, we'll call it hypochlorous acid HA. If you're going to do this, I do expect you to mention, okay, HA is this, right? So for the initial concentration of sodium hydroxide, we take volume 1 on top. Volume 1 is our volume of sodium hydroxide, 40 milliliters, right there. Molarity 1, our initial molarity of sodium hydroxide is 0.2 molars. Goes right there. Volume 2 is the total volume, 60 milliliters. Goes right there. So we've got 40 times 0.2 divide by 60. And we get that our concentration for sodium hydroxide is 0.13333. So rounded to 2 sig figs, it's 0.13 molar. Now, for the weak acid, molarity, volume 1, 20 milliliters of hypochlorous acid. Molarity 1, 0.4 molars, goes right there. Volume 2, the total volume, 60 milliliters. And so 20 times 0.4, 20 times 0.4, divide by 60 equals 20 times 0.4 divide by 60 equals 0.1333. So now we can already see we are at the equivalence point actually. The molarity of our base is exactly equal to the molarity of our weak acid. And so they are going to completely neutralize one another. That is because we're at the equivalence point. So now let's move on to the step 1, stoichiometry. Same equation as before. We have the acid neutralizing with the base. So our reactants are the hypochlorous acid and the sodium hydroxide that we added to it. Reminder from the last slide, sodium hydroxide concentration 0.13 molar, weak acid concentration 0.13 molar. The weak acid, the sodium hydroxide is being added to the weak acid. So our reactants are sodium hydroxide and weak acid. We're going to assume 100% reaction till either the sodium hydroxide or the weak acid is all gone. And what we will produce is the salt NaA and water from the H plus and the OH minus. Normal neutralization reaction. We're going to set up not an ice table, but a start, change, end of stoichiometry table. Before we do that, to clean it up, let's remove the sodium spectator. So we've got not sodium hydroxide, but just hydroxide ions. For the NaA, we have just the A minus, so we've removed the Na plus now. Looks a little cleaner. I like to remind myself what I'm focusing on is the conjugate base. Is the sodium there? Yes. Is it doing anything? No. Sodium ions are just floating around in water doing nothing. Really helps to remove the spectator. Okay, and so now we set up our start, change, end of stoichiometry table. Our initial concentrations of the weak acid is 0.13 molar. For the sodium hydroxide, it is 0.13 molar. For the conjugate base, we have none. And this because this is before the neutralization happens. And so now, the way we decide what happens is whichever we have less of, the hydroxide or the weak acid, it's going to react till it's 100% gone. In this case, it's both of them. So the sodium hydroxide is going to react till it's all gone, so there's 0 left. So 0.13 molar will react because 0.13 minus 0.13 is 0 molar. Also, 0.13 molar of the weak acid will react, and so there will be none of the weak acid here. This means we are at the equivalence point. We have added exactly 1 mole of base for every 1 mole of acid. So the weak acid has been completely neutralized. All that is remaining is its conjugate base. So over here on the product side, we'll put plus 0.13. So our concentration is 0.13 molar of the conjugate base. Now here's where you need to think. For my next step, the equilibrium. What is the equilibrium that's happening? Well, the only thing that is in solution is our conjugate base. When you're at the equivalence point, the only thing left is the conjugate. So what we have in the solution now is the conjugate base and water. Those are going to be our reactants. Okay, what we want to write on the reactant side for our equilibrium step is what is actually in the solution now. It is the conjugate base and water. These will be our reactants for step 2. So step 2, equilibrium. From the previous slide, we have that concentration of our weak acid is 0 molar. Concentration of our conjugate base is 0.13 molar. Notice what we wrote here. We don't have any weak acid in solution, so it's not appropriate to write the weak acid as a reactant. What we actually have is the A minus. That is the reactant, along with the water. There's plenty of water there. Now remember, A minus is the conjugate base of a weak acid. So it itself is a decent base, and so it's going to behave like a base and accept a proton from water. And so the result is that you will get H plus and A minus, which gives you the conjugate acid of A minus, it's HA. And what remains of the water is that it has lost an H plus, so it's hydroxide. 1 hydroxide down one charge unit from 0 down to -1. And so that is the appropriate equilibrium equation to write here. The hardest part of these problems is getting this equation right. Once you got that, now we just continue like we're doing an equilibrium problem in chapter 18. We're going to make an ice table. So here's just words saying what I just said. So the K for by the way, the K for this equation is not the Ka of HA. It's the Kb of its conjugate base. So we're going to need to find the Kb of the anion, hypochlorite ion. You guys remember how to do that? You can't look it up from a table, but you can figure it out based on the Ka. The Kb of hypochlorite ion is going to be the Kw 1 times 10 to the minus 14 divided by the Ka of its conjugate acid, HA. And so our Kb here is going to be 1 times 10 to the minus 14 divided by the Ka of HA, which is 2.5 times 10 to the minus 4. And so we get a Kb of, for the conjugate base, of 4.0 times 10 to the minus 7. Okay, and that's going to be the K for this equation you see above. So, all right, you can kind of see it behind my head still, right? All right. Now, our initial concentration of the conjugate base is 0.13 molar from the last slide. Our concentration of hydroxide is going to be close to 0. Our concentration of our weak acid is now 0. We're at the equivalence point. And so this reaction must go forward. It can't go backwards because there's no products. So we're going to have minus 0.13, right? Or sorry, not minus 0.13. Minus x here. Not going to be 0.13. There's a weak base. Minus x here, plus x here, plus x here. So our equilibrium concentration is 0.13 minus x, and then x for hydroxide and x for the weak acid. Another thing to keep in mind here is that a lot of times people forget x is hydroxide in this case. We're going to have a little bit of an extra step in calculating the pH because we're going to start with the concentration of hydroxide once we solve for x. We can't use the Henderson-Hasselbalch equation, okay? Don't try. HA is 0. We do not have a buffer. We do not have a mixture of the weak acid and its conjugate base. We have just a weak base here, equilibrium, for this A-. So we have to write Kb. The Kb expression is going to be hydroxide times the weak acid concentration on top. On the bottom is going to be the A- concentration. And so that's going to be x times x on the top. And the bottom is going to be 0.13 minus x. And that is equal to the Kb right here. Kb 4.0 times 10 to the minus 7. So now we're going to take all this, we're going to carry it forward to the next slide. So Kb is concentration of hydroxide over concentration of weak acid. It was Kb was 4.0 times 10 to the minus 7. And we had x and x here, and then 0.13 minus x. And so pre-check 0.13. So we do our initial concentration divided by the K. Is that greater than 400? Oh yeah, way greater than 400. So on the top, we'll call this x squared. On the bottom, we'll say 0.13 minus x is about the same as 0.13. X will be small. So now we will multiply both sides times 0.13 when we're trying to solve for x. So that will cancel, and we'll get x squared equals 0.13 times 4.0 times 10 to the minus 7. So to solve for x, we're going to multiply these and then take the square root of both sides. So let's do that. 0.13 times 4 10 to the minus 7 equals this. And now we're going to take the square root of that to get x. Square root of answer equals, and we're going to get 2.3 times 10 to the minus 4. That's x. And that is the concentration of hydroxide here. So what we can do is we can get the POH first. So the POH is a negative log of the hydroxide concentration. So that's a negative log of 2.3 times 10 to the minus 4. Let's do that. Negative log 2.3 10 to the minus 4 equals, and we get a POH of 3.64. 2 after the decimal because our number that we took the log of had 2 sig figs. So 3.64 is our POH there. Then POH and pH add up to 14. So pH is going to be 14 minus the POH. And so 14 minus 3.64, that is 10.36. Remember to go 2 after the decimal because 14 is exact here. So we're going to stay 2 after the decimal. Our pH is 10.36. Now let's do a reality check. This is a strong base, weak acid titration. You should ask yourselves, at the equivalence point, which is where we're at, what should the pH be? For a strong base, strong acid titration, pH was 7 at the equivalence point. This you should understand from our concepts we talked about earlier. For a strong base, weak acid titration, the pH will be greater than 7 due to the presence of the A minus here, the conjugate base of the weak acid. It causes the solution to be basic at the equivalence point. And indeed, we got a basic pH, so that at least checks out. Okay, so that's how you approach a strong base, weak acid titration when you are at the equivalence point. What about the next one, when we go beyond the equivalence point? So once we go beyond the equivalence point, what we're doing is neutralizing all the weak acid, then we're dumping in strong base. So after the equivalence point, the pH is going to be dominated by the strong base that we are adding. We'll have the weak base A minus still in there, but its contribution to the pH is going to be very small compared to the strong base hydroxide we're continually adding. But we're going to follow the same procedure. First thing we're going to do is get initial concentrations. We're going to do this by the dilution approach, which again is different from your book, but I like to do it this way. I think it's better. So our total volume is going to be the 20 milliliters of hypochlorous acid we started with, plus the 60 milliliters of sodium hydroxide we added. So the volume total is 20 milliliters plus 60 milliliters is 80 milliliters total. And that is volume 2. So for sodium hydroxide, our volume 1 was 60 milliliters. That's how much we added. Our molarity of the sodium hydroxide is 0.2 molar right here. Our total volume, volume 2, is 80 milliliters right there. And so it is, our concentration is 60 times 0.2 divided by 80. That equals 0.15 molar. Now, for the weak acid, our volume 1 is 20 milliliters. Our concentration, our molarity 1, is 0.4 molars to begin with. Our volume 2 at the end is 80 milliliters. So our concentration is 20 times 0.4 divided by 80. Basically, 20 divided by 80 is a quarter. So 1/4 of 0.4 is 0.1. So now you can see that we have significantly more strong base than we had weak acid. So let's do our stoichiometry step, neutralization, to show what's going on here. Okay, and so step 1, stoichiometry, just like before, we're calling the weak acid HA. The weak acid is being combined with sodium hydroxide. And from the previous slide, we have sodium hydroxide concentration initially is 0.15 molars. For the weak acid, it's 0.10 molars. The weak acid and sodium hydroxide, those are what are being mixed. And just like before in the previous stoichiometry steps, the salt is sodium and with the anion here, NaA, and our other product is water. We remove the sodium spectator. We don't want it, so no sodium plus here, no sodium plus here. That leaves us with hydroxide and A minus right here. Then we set up our start, change, end of stoichiometry table, and we put in our initial concentrations. Initially 0.1 molar of the weak acid, 0.15 molar of the hydroxide, and for the conjugate base, we're starting with none. So we're assuming that this is going to happen first, then we'll deal with what's there. So now, actually, it's the weak acid that's going to run out first. So we can't use up all the hydroxide. So what's going to really happen is this is going to react till one of these two run out. What's going to run out this time is the HA. So our X here is going to be 0.1 minus 0.1. That leaves us with 0 of the weak acid. So the reaction cannot go any further. And so we'll also lose 0.1 molar of the hydroxide, leaving 0.04 molar of the hydroxide. And then we'll do plus 0.1 molar for the anion here, and we get 0.1 molar. So what we've got in the solution now past the equivalence point. We got 0.1 molar of the anion, but we have 0.05 molar of hydroxide. So going back, okay, let's compare the molarity or the pH of the solution when we had the weak acid, or the molarity of the hydroxide when we had the weak acid compared to 0.05. Okay, let's go back and look. The molarity of hydroxide when we did the weak acid equilibrium was 2.3 times 10 to the minus 4. Extremely small. 0.05 is so much bigger than that. This amount of hydroxide that is contributed by the A minus acting like a base is negligible. So we're going to just focus on the 0.05 molar of hydroxide. That is going to dictate our pH. This is so little of a factor it doesn't matter. That's the assumption for after the equivalence point. It's the excess strong base that is going to decide the pH. So from the previous slide, we have 0.05 molar sodium hydroxide or hydroxide ions, 0.1 molar of the weak acid. We have excess strong base because we're after the equivalence point. So past the equivalence point, the excess hydroxide dominates because hydroxide is a much stronger base than the anion. So if we want the POH, we just take the negative log of this hydroxide concentration. Contribution of the conjugate base is negligible. So our POH is going to be the negative log of the hydroxide concentration. So negative log of 0.05. So negative log 0.05 equals 1.30 for the POH, or 1.3 actually, because this has one sig fig. And finally, pH is 14 minus POH, so 14 minus 1.3, that is 12.7. So yes, the A minus does contribute a little bit to raising the pH, but the hydroxide is really where it's at. So when we go past the equivalence point, what we pay attention to is the excess amount of strong acid, or in this case, strong base, because that's the titrant. And that is how you approach a strong base weak acid titration at each of the points in the titration. Before the titration starts, then after the titration starts, but before the equivalence point, at the equivalence point, and then after the equivalence point. Notice that the first step is always the same. It's the neutralization. It never changes. But the second step, the equilibrium step, it all depends on where you're at in the titration. So remember that. Practice this. Doing this one problem won't be enough, okay? But I did want to walk you through exactly how to do one problem at every stage of the titration. So hopefully this has been helpful. As you can see, when you're first doing them, they take a while. So make sure to practice with the problems in the book as well. And I will see you guys at office hours. Have a good one.